Okay, David, you've spent the last 6 or 7 years, I believe, working on this radical proposal for the reformulation of fundamental physics in terms of something that you call constructor theory. So I'd like to know what on earth constructor theory is and how you got started thinking about it.
The way it began was actually significantly different from the way we think about it now.
Okay.
I had been working on the quantum theory of computation and information, and at the time I thought of that as like the fundamental theory underlying all physics in a sense, because the universal quantum computer can simulate the behavior of any other physical system, and therefore in a sense the whole of physics, the behavior of all physical systems, is just the study of that is the same as the study of the programs of a universal quantum computer. But then I realized that that was actually inadequate, that actually quantum theory of computation doesn't underlie everything, because when you want to study the behavior of a particular physical system and particular physical laws that system obeys, you have to know which quantum computer program corresponds to that. And that's that theory of which is which, that's what really corresponds to the whole of physics.
Okay.
So I set about trying to extend the quantum theory of computation in a way which would encompass that as well. But the more I did that, the more I realized that the conventional way of understanding computation and physics was inadequate to this task. The conventional way being that you have initial conditions, which for a computer corresponds to the program, and you have laws of motion, which in a computer corresponds to the elementary operations by which the computer works, and then between those they tell you what happens at all times. But that wasn't adequate to describe simple things like information in more general terms than in the quantum theory of computation. So then I gradually realized that what's needed is just a new approach to fundamental physics, as well as to fundamental computation. And the idea there is that instead of having initial conditions and laws of motion which then tell you everything, everything that happens, instead you step back a bit and you have a theory of what can and can't happen, what's possible and impossible. And what actually happens is then just an emergent property of what can and can't happen. And that's constructor theory.
Okay, so one of the motivations for constructor theory is that it enables you to bring these things like computation and life and information and thermodynamics into fundamental physics.
Yes.
And I wonder if you could talk a bit more about those areas and how they end up in your picture.
Some of these emergent things are emergent and inexact in fundamental physics, not because they are in nature, but because fundamental physics can't deal with them intrinsically, can't deal with them exactly.
Right.
And ironically, or appropriately, depending on which way you look at it, computation itself is one of those things. Because to define a universal computer, which is at the center of any kind of computation theory, you can't define it by just what it does, what it does in fact, in reality, because universal refers to all the things it could do.
Right.
And the theory of computation is basically the delineation of the difference between the things it can do, could do, and the things that it couldn't possibly do, the non-computable functions, the undecidable problems. And that partition, with the benefit of hindsight, is central to the theory of computation as well, including quantum computation, but it wasn't thought to be central to physics. So that's one of the things that we're taking over from computation to physics, the idea that that what really matters is for understanding a physical system is understanding what it can and can't be made to do, not just what it can and can't do, what it can and can't be made to do.
Right.
And what it actually does is kind of contingent. That's not as important. It's an emergent property. It's the other way around from the way physics is normally construed.
Okay. So if I understand you correctly, in theories of computation, you work from kind of a few axioms about the kinds of things computers can do through to proofs of what programs are possible or impossible.
Yes.
And that's really what you're trying to extend to physical reality. That's why constructor theory is a theory of principles from which you derive the rest. Do I have that correct?
That's exactly right.
Okay, great.
There's a famous quotation by the physicist Eddington, who said that the laws of thermodynamics, especially the second law, are more fundamental than anything else in physics. He said, if your theory violates the law of conservation of energy or whatever, then you will say so much the worse for the law of conservation of energy. But if it violates the second law of thermodynamics, then there's nothing left to do but for you to withdraw in shame. Something like that.
Okay.
And therefore, in some sense, the thermodynamic laws are deemed to be more fundamental. But in another sense, in the sense of the way that theories in physics have been built up, it's not only is it not fundamental, but it can't belong to fundamental physics at all. It is deemed to be inherently approximative, inherently emergent, and to the extent that the moment you describe a system exactly, in other words, according to the laws of physics, according to its laws of motion, you lose the opportunity to describe thermodynamics on that system.
Okay.
Now, this is an artifact of the initial conditions plus laws of motion conception of physics. And it just goes away in constructor theory. And Chiara Marletto has produced a very nice foundational theory of thermodynamics based on an old theory of Caratei-Dori, which again no one knew how to incorporate into fundamental physics, but everyone was saying, oh yeah, this has got to be the way to go, but they didn't know how. And I think that she has managed to do it.
Okay.
And it's because of this simple difference, apparently simple difference between how constructor theory views the foundations and how the prevailing conception views them.
Okay. But I'm always baffled by the motivation for that, because what if it's just the case that thermodynamics is an emergent phenomena, and what evidence base do we have that requires moving it into fundamental physics?
Well, all science is conjectural. It could turn out that thermodynamics isn't fundamental. It could turn out that constructor theory is false. But we have these clues, like I said, the Eddington conception, and also the fact that there are various clues from different parts of physics that strongly suggest that thermodynamics is a fundamental part of nature. One of them is black hole physics. Stephen Hawking and before him Jacob Bekenstein showed that a black hole has thermodynamic properties such as entropy, which the black hole entropy, however, is an exact property of the black hole. It's equal to just basically a constant times the mass of the black hole. And this entropy can appear in thermodynamic equations along with normal entropy. And yet the normal entropy is approximative and the black hole entropy is exact. So it's not. So some people say, well, it's not really entropy, it's just pseudo-entropy. But the thing is that the thing that has to increase is the sum of the black hole entropy and the normal entropy, not just the normal entropy.
Okay.
So it really fits into the laws of thermodynamics in an integral way. So that's another clue. I mean, again, this could be an anomaly that's explained in dozens of different ways. Somebody could come up with a different theory. Could say that the black holes don't have real entropy, or in a million different ways. But it's suggestive, and like all motivations for theories, that they are not proofs. They're not even proofs that the theory is needed or that a theory is needed, but they are starting points for a research program.
Right.
And when you find that there are several different ones of these motivations leading to the same conclusion, and that conclusion is simple, then you're led into studying it whether you like it or not.
Fair enough. I gather another such motivation has to do with the limitations of what Lee Smolin calls the Newtonian paradigm. Are you aware of that phrasing?
No.
He says that, and you say it too, I think, that when you analyse the universe in terms of initial conditions and laws of motion, that rules out explaining what the initial conditions were, because you can't explain the initial conditions in terms of a model which includes the necessity of initial conditions.
Yes.
And constructor theory might be able to do that, you believe?
Oh yes, well, if constructor theory works, it will have to do that.
Okay.
Because when I said that what actually happens will emerge as an emergent property, that includes the initial conditions. So constructor theory is based on this dichotomy between tasks that are possible and tasks that are impossible.
Such as?
The possible ones might include the building of a universal computer.
Okay.
And the impossible ones would include the building of a perpetual motion machine of the first kind or the second kind.
Okay.
But now, if we focus on the possible ones, a task being possible means that that building a constructor to perform the task is possible, which means that there must be raw materials suitable for building such a constructor, which means that the initial conditions of the universe must be such as to provide such raw materials, not just once, but generically, because possible and impossible have to be universal concepts. So generically, we have hydrogen or protons and so on, and it must be possible to get from that to whatever the theory says is possible.
Okay.
So therefore, if constructor theory is to be self-consistent as a universal theory of physics, it has to explain initial conditions, albeit only emergently, like it will describe laws of motion emergently.
Okay, I think I get it.